So good morning. Today we'll continue with chapter 2, that is bipolar junction transistors. All right. Share. And I introduced the topic last class. So just a brief recap. We looked at the PN junction diode, where you have a P-type semiconductor and a N-type semiconductor brought into close contact, functions like a vacuum tube diode, hence the name of that semiconductor device, PN junction diode. In a transistor, you actually have two PN junctions. So there is a PNP transistor and an NPN transistor. Both of those have a sandwiched layer between two semiconductors of the same type. So in a PNP transistor, you have an N-type junction in the middle of a P-type material. And in an NPN transistor, you have a P-type material between two N-type materials. Okay. The symbol for a transistor is shown in these images right here. Typically, we do not have a circle around the symbol. Some textbooks and some authors do like to use those circles, but typically we simply have a transistor that is drawn like this. Okay. You have a straight vertical line. Well, depending on how you orient the transistor, obviously. You have a straight line and two angle lines. Okay. And one terminal has an arrow either pointing out or pointing in. If the arrow is pointing out, it's an NPN transistor, as you see here. Arrow in. That arrow notes the direction of the current flow for the entire device. Okay. So this is out and this is in. So when you draw out the transistors, that's, the small arrow is very significant. Okay, so we have an NPN transistor, we have a PNP transistor. Let's see what happens in operation. So this is a actual cross-section. So this is a cross-sectional image of an actual transistor. And you have one of these. If you're taking the lab, you have one of these in your lab kits. I also have some around here in the room. Basically, this is a package. So the black material that we see here is simply the package encapsulated inside. The actual transistor is right here.
That'd be so boring.
Is right here.
Just turn down the volume a little bit.
Yeah.
You don't really.
Okay. So as I was saying, the actual transistor is right here. Okay, it's very tiny. So the transistor itself is very small. The package leads require that the actual package is really big. Okay. And that's the case with almost all integrated circuits, all ICs, all microchips. You have a package that seems of a large size compared to the actual device or the actual microchip. The reason is because we have a number of pins, number of connections coming out from those devices. So this portion right here is shown in the next slide. And you can see here, even in that device, the biggest size is taken up by the contact terminal. Okay, contact terminal. So packaging and bonding, again, just going on a little bit of a tangent, packaging and bonding of microfabricated devices is a specialty by itself. Okay, it requires a lot of design, a lot of analysis to actually package a microfabricated device. The reason this is large is, again, because we need to make connection with the outside world, meaning you have larger circuits, you have power supply terminals, you have other circuit components that need to make contact with this micro device. And so this is an interface between the microchip or micro world and the macro devices outside. Okay, that's the reason why it's so big. The actual transistor is right here. And even in this small piece of silicon that you see, the actual transistor would be much smaller in size, probably about the size of the gold bond that you see. Okay, so you have a gold bond wire on top making contact with the other side of the transistor device. So this is just a cross section. Okay, this is just a cross section. If you look at it from the top, this is how it looks. And this is, of course, a zoomed in image under a microscope. Okay, a zoomed in image. So from the side, you see a stack layer and you have a silicon die, right? That's a cross section. But it's still not showing you the actual cross-sectional device of the silicon. It's just showing you a cross-sectional slice of a real-life transistor. Okay, and this is a real-life transistor looking at it from the top. So when you look at it from the top, you can see everything is constructed in one single plane. Okay, this is the X and Y axes, and we are not able to see the Z. We cannot see the Z. It's just so small. Okay, we simply have to visualize it. All right, so here is a construction of a simplest or a simple transistor, and this shows you the side view. In microelectronics, we typically work with side views just to show how it is actually constructed. So if you looked at this from the top, it would look something like this. So you have a rectangle, and again, this rectangle again is a small piece of the entire silicon wafer. And this entire piece is N-type material. It's N-type material. So that's side view. This is the top view. I'll just spend a few minutes doing this, but then after that, again, as non-E majors, we are more interested in looking at circuits using these transistors, not the transistor construction itself. So if I look at, so this would be all blue. I'm going to shade this. Okay, so the region outside is all N-type material. Okay. And then you have the P-type material inside this. Okay, so this is all P-type. And then you again have the N-type material inside. Okay. Does that make sense? The side views and the top views. An important note, all semiconductor fabrication takes place from the top view. Okay. The side views are very small. A typical 4-inch silicon wafer is only about 0.5 millimeters thick. 0.5 millimeters. That's the size of the diameter of the mechanical pencils that you use. Okay, so an actual silicon wafer, a 4-inch silicon wafer in diameter is only about 0.5 millimeters thick. At the micron scale, 0.5 millimeters is 500 microns. And out of those 500 microns, we typically use only the top 1 micron or 2 microns of the surface. So just to give you an idea, you're going inside the wafer, inside the silicon wafer in this direction. And it goes all the way to 500 microns or 0.5 millimeters. Okay. And this right here is the surface. This is probably 1 or 2 microns. And even 1 micron or 2 microns is considered 1 to 2 microns is also considered deep. Okay, it's considered deep. So anyway, that was the N-type material. That's the P, and this is P. That's the base, and this is inside is again N E. Okay, so you have a NPN transistor. You have the side view and the top view for a NPN transistor. PNP transistors also work the exact same way, but for most of our discussions, we will work with NPN transistors. The only thing is everything will be exactly the opposite. Electrons will be replaced by holes, holes will be replaced by electrons, current direction will be opposite, biasing will be opposite. So typically, even when we teach these classes for EE majors, we only discuss NPN transistors, and the rest is, well, basically assumed or up to the student to review. Okay, so you see 3 connections, NPN transistor, EBC. The EBC stands for emitter, base, and collector. Okay, emitter, base, and collector. And these are, of course, not to scale. So I need to ensure, write those down there. These images are not to scale. They're completely blown up and out of proportion. Okay, so you have 3 terminals, emitter, base, and collector. And when we go to the symbol for a transistor, the arrow notes the emitter. Okay, the arrow notes the emitter. Emitter and collector, as the name suggests, they emit charge carriers and the collector collects the charge carriers. And the base is the region that controls the charge carrier flow between the emitter and the collector. And that's also the basic principle of operation for a transistor. So, NPN transistor, we would think that they would, since we have 2 PN junctions, they would behave like exactly like 2 PN junction diodes. But that's not how it actually works. The reason is because of the actual physical construction of this device. If you see in the figure, again, as I stated, that these are not to scale, the reason I'm emphasizing that is because the base terminal or the base region of this PN junction diode is very, very thin. It's very, very thin. So here we think that these are 2 PN junction diodes, but they don't exactly work like 2 PN junction diodes. Okay, there are 2 excuse me, there are 2 diodes connected back to back, but the operation depends on the external voltage that we apply to these devices. Okay, and that, of course, is known as biasing. For our diodes, we have 2 modes of operation, forward bias or reverse bias. For transistors, we have 3 modes of operation. So similar to the analyses we perform for diodes, we would make an assumption and we would verify whether that assumption is correct or not. It's only 2 possible states. 1 junction, 2 possible states, either forward bias or reverse bias. For a transistor, we have 2 junctions, we have 3 possible states. And we'll talk about those 3 states in just the next few slides. But let me go back here. So in this physical construction, what happens is a collector, this is the collector. It is lightly doped. Okay, it's lightly doped. Lightly doped means there are not a lot of impurity atoms in that semiconductor material. Remember, doping is the process of introducing impurity material inside your semiconductor, right? The more impurity materials you have, the more charge carriers you generate to conduct your electricity. So if it's lightly doped, you have less charge carriers. It's heavily doped, you have a whole lot more charge carriers. So the collector junction is always lightly doped. The base is very, very thin. So this base region is very thin compared to the other two. Okay. The emitter is the smallest of all three areas, but it is the most heavily doped. And hence the name emitter, right? It emits charge carriers. And when you have heavy doping, means you have a whole lot more impurities inside that region. There are extra charge carriers. There are extra charge carriers that are able to conduct electricity. Okay, makes sense so far? Any questions? Let's take a pause. Let me know if you have any questions. Okay. All right. One final note about this is that sometimes we refer to the doping by a notation of plus. So we could say N plus means there are more charge carriers than a certain level. Okay. And then you have P plus. And then here the emitter can be labeled as N plus plus. That notation simply indicates that it is very heavily doped. That's all. Okay. So the plus plus indicates it's very heavily doped. Okay. So because the base region is very, very thin, we bias the diodes, depending on the application, of course, we bias the two PN junction diodes in different ways. They could either both be forward bias, they could both be reverse bias, or one of them could be forward bias and reverse bias, which is the majority of our applications. Okay. If we wanted to bias this for, let's say, for use as an amplifier, right? Actually, you know what? Let's talk about biasing later, just in the next slide. Base region is very thin, right? Emitter region is the most heavily doped. So when charge carriers go from the emitter to the collector, we can use the base, you can use the base charge carriers to control the flow of the charge carriers that go from the emitter to the collector. Okay. So if charge carriers, meaning electrons or holes, are going in this direction upwards, then current is coming down. Right? Charge carriers go up. And current is the opposite of the flow of electrons. So current is actually coming down. Okay. So if current is coming down, we can apply KCL, and you can consider the transistor as a T. You have IB coming in, you have IC coming in, and you have IE leaving. So you can apply KCL and obtain the equation IE. The emitter current is the sum of the base and the collector currents. Okay, so IE is IC plus IB. And if you think in terms of nodes for the three terminals, you have three voltages. So you have from here, actually, let's just do three nodes. This is VBC, voltage at the base measured with respect to collector, or you can write it as VCB. Either ways. And then you have base to emitter, VBE. You apply KVL, and you can obtain this equation. So this is from KCL. This is from KVL. Analysis techniques do not change. The techniques are still the same. It's only the device that is new. So we study the device, but the techniques that we apply are still exactly the same. So we can see the emitter current is the sum of the collector and base currents, and the collector to emitter voltage, VCE, is the sum of the other two voltages. So in the next couple of pages, I will explain the basic operation of a bipolar junction transistor. Before that, let's take a 10-second pause. Let me know if you have any questions. Yes. It does, depends on the application. So right now we are using VBC and VCB kind of interchangeably just because of the signs. But depends on the circuit, depends on the application. Pretty much the theory behind this, not theory, it's simply to apply KVL. We're just trying to say that the two voltages added up together give you VCE, or basically the emitter and collector voltages. And then the two currents summed up together give you the emitter current. So KCL and KVL. So the question being asked was about whether the sign matters or not, whether we take VBC or whether we take VCB. Okay, reference changes. Other than that, it's fine. Okay, so fluid flow analogy can be made. You have collector current coming in and going towards the emitter. The emitter current is the sum of IC and IB, collector currents, and the base current. And the base current is actually controlling current flow in the BJT. So it's a valve that is controlled by the base. The valve will control the flow of current from the collector to the emitter. Okay. So remember the diode where we had a one-way valve. Fluid flow can be possible only in one direction. The other direction, the valve is closed. So the same fluid flow analogy can be made for a transistor, meaning you have a pipe. The pipe is conducting fluid, and you have a controlling valve somewhere in the middle. That controlling valve will open and shut. And depending on our application, you can control the flow of fluid through that pipe. Okay. So basic operation again, here's more detail. You have electrons and you have holes in this NPN transistor. N plus simply means it's slightly higher doped. Base is very thin and lightly doped. And you have a very, very heavily doped emitter region. This is an NPN transistor. So the emitter has an excess of electrons a huge number of electrons or free electrons that are free to move about. The base is very thin. Physically, it's very thin. Plus, it is lightly doped, so it doesn't have as many free charge carriers. And because it is a p-type material, that means it has holes. Okay, it has holes. And then you have the N plus, meaning it's a level above lightly doped and quite a few levels below heavily doped. And it's an N-type material, so you have electrons here, and you have positive holes here, negative over there. Okay, so this is what happens. You take two voltage sources and you apply external biasing to this. Okay, so if you connect an external source, this is minus, this is plus. Actually, let me use the red ink. This is minus, this is plus, this is minus, this is plus. What do you notice? Let's take the emitter base PN junction. What mode of operation is the emitter base PN junction? Anyone? Negative is applied. Sorry, what? So we are applying an external voltage source to this PN junction, right? We're connecting here. So it's a PN junction diode. So if it's a PN junction diode and we apply the voltage as shown in this figure, what is the mode of operation? Is it forward bias or is it reverse bias? N, P, N. The negative end is applied to N, so it's forward bias. So the emitter base junction is forward bias, whereas the collector base junction is reverse bias. And that's where the magic happens. It's reverse bias. So we would expect if it's reverse bias, there shouldn't be any current coming out of it. But due to the actual physical construction, and again, repeating that the base is very thin, the forward bias PN junction on the left will send a huge amount of electrons flowing across the first junction into the base. Make sense? The PN junction, excess of charge carriers, excess of electrons in the emitter, and they cross over into the base region. The base region, two factors, physically very thin and electronically devoid of charge. Well, not devoid, but very few charge carriers available. And the charge carriers that are available are holes, positively charged holes. So some of the electrons from the emitter jump into those holes. Again, remember, hole is a positively charged particle, but it's physically it's an empty spot. So some of the electrons jump into the spots and take out one positive charge and one negative charge, which is the process of recombination. Right? Electron moves into a hole, that gets rid of the electron, also gets rid of the hole. Recombination. There are not enough holes for the charge carriers to recombine. Plus, the base region is very thin. So when you reverse bias this, a lot of the electrons have sufficient energy to not go into the base, but flow into the collector region. This is the emitter. This is the base. This is the collector. So again, huge number of electrons cross over into the base region because the base region is very thin. Some of the electrons will recombine with the holes inside the base, but a majority of the electrons will cross over the second PN junction and go into the collector. So the collector is receiving or collecting the charge carriers, or the electrons in this case, and hence the name collector. Okay, let's take a 10-second pause. Will you think over that? Let me know if you have any questions. Any questions? And this is very important to understand. Standard BJT, one PN junction behaves like a standard PN junction diode. The other one doesn't. It's a reverse bias. In reverse bias, you would expect there is no current flow or very minimal current flow. But because of the actual physical construction of the transistor, there is a huge amount of current that's actually flowing through that collector junction. And the reason is because a large number of electrons cross over into the collector junction. That's just the basic operation. Okay. As far as semiconductor physics goes, this is as far as we'll talk about it. Because again, not a major class, we want to move on to actual circuit analysis. So the relationships between the different quantities are quantified or noted by two terms, alpha and beta. Alpha stands for the ratio of the collector current to the emitter current. And beta, the most important, is the ratio of the collector current to the base current. Okay. This is a standard specification of a BJT. So if you buy a BJT off the shelf from a manufacturer, these two are part of the spec sheet. This is the current amplification factor, IC over IB. IC over IB can be far greater than 100. Okay, even the cheapest transistor made would have a beta of more than 100. Typical values of alpha is about 0.99, and I will explain how and why. Approximately equal to 0.99. If you go here, IE is IC plus IB. IB is very, very small, typically in microamps. Okay, so if you ignore this, IC and IB are approximately equal in value. Okay, IE is approximately the same as IC, except for a small amount of base current. And so we see that here. The base current is very, very small. Orders of magnitude smaller than the collector current. So the emitter currents and the collector currents are very similar, except IC plus IB is equal to IE. So it's not quite 100% equal, slightly less, about 99% or so. Hence, alpha value is about 0.99. And then beta, of course, is the current amplification factor, meaning you apply a small current at the base terminal, and you can control the flow of current going from collector or between the collector and the emitter. And that is the principle of operation. A vacuum triode, a vacuum tube triode, was nothing but a vacuum tube diode to actually control the flow of current or electrons between the cathode and the anode. So it's the exact same operation or principle. You inserted a third element, not element, but third, a third junction, not junction, third slice of semiconductor material to control the flow of currents between the collector and the emitter. Okay, and that's where we get our regions of operation. All right, 10-second pause. Let me know if you have any questions. Okay. So what are the modes of operation? Well, 3 modes of operation, right? As I said, you have both of them reverse bias. You can have both of them forward bias. You can have one forward and one reverse bias. So there are 2 modes of operation that you can use together in a circuit, cutoff and saturation. And you can use it as a digital or electronic switch. Electronic switch. And then between the 2 modes of operation, you have the active mode. The active mode is where you can use it as an amplifier. Remember, a small amount of current coming from the base is controlling the actual flow of current from the emitter to the collector. And so the logic being that the small amount of current from the base will give it shape to the emitter and collector currents. These regions plotted on a characteristic look like this. You have the saturation region on the far left, the cutoff region right here at the bottom, and everything else is the active region. Okay, active region. Cutoff region means, as the name suggests, very minimal current flow. Everything goes to 0 or as close to 0 as possible. Saturation means the switch is wide open. Everything is fully flowing. It would be the solid state version of a mechanical light switch. Light is off. I mean, the switch is off. No current flows to the light. Light is off. If the switch is flipped on, current goes to the light. Light turns on. So cutoff region is basically where it's off, and saturation is where it's on. An active region is where we use the amplification factor of a transistor. Look at the units, the unit prefixes of the input base current. They're all in microamps. Okay, microamps, 10 raised to minus 6. Whereas the output collector current is in milliamps, 1,000 times more. Okay, it doesn't seem like it. It's a small difference between a micro and milli. There's a huge difference, 1,000 times. Make sense so far? Any questions? So I always get the question from students at first when they are learning this for the first time, what does it actually mean to amplify, right? Amplify simply means, okay, if you give 1 and the amplification factor is 10, you should expect 10 the output. If you give in 100, you should expect 1,000 at the output, right? So where is that energy coming from? So here's how I like to explain. Let's say you have an amplifier device, any kind of amplifier. Okay, we're not talking about like a microchip or a transistor or like a AVR, just an amplifier, sealed box. We don't know what's inside it. That amplifier would have, well, electric power. Let me see. Right? and you'd apply a signal to it, like an audio signal or something to it. And what is it, that audio signal? Some sort of signal, which would typically in milliamps or millivolts. Very, very small. So let's say you have a signal that looks like this. And this signal is 1 millivolt size. Okay, 1 millivolt in size. Okay, this has nothing to do with like circuit analysis or anything. I'm just explaining what amplification would mean in this case. So let's say your device, amplifier, whatever you have, the amplification factor is 1000. Is 1000. So you would expect, if you apply 1 millivolt, you should expect 1 volt at the output, right? 1 millivolt times 1000 should give you 1 volt. What if you apply 1 volt? Would you get 1000 volts? No. Where is the energy coming from? The energy is coming from your power outlet. Inside it, you convert it to DC. So the amplifier, all the amplifier is doing is it takes the DC source plus the AC signal and adds them together. And that is the output of the amplifier. It takes the DC supply and it gives the DC supply the shape of your AC signal. So if you have a tiny signal and you add it to, let's say, a DC signal of 10 volts. Let's say this is 1 millivolt signal, and you add it to a DC signal of 10 volts. The amplifier has now taken that DC signal and given it the shape of the AC. And that's what the amplifier is doing. And that's what it means when we say the base controls the current flow through the collector and the emitter of the transistor. Okay. If the shape of the signal going into the base is a sinusoidal waveform, then the current flow coming out of the collector will also take the shape of the base sinusoidal waveform. So in a sense, in the most simplest of terms, your transistor is adding the DC and the AC components together and sending it to the output. Okay, that's where it's coming from. So when we say it's amplifying, it's not, the energy is not coming out of thin air. It amplifies, but the amplification comes from the external energy sources that we connect to our transistors. That's where it's coming from. And that's the hardest concept for first-time students. I mean, not just non-EE majors, even EE majors. This is the hardest concept, to grasp. It's not coming out of thin air. When we say that the base is controlling the current flow, meaning if you apply any sort of signal to the base, it is giving the shape of that incoming signal to the external DC bias that is applied to the transistor. And hence, it results in an amplified. See, if the base, if you just give like a 1 volt flat line, you would obtain a higher value, a higher level of flat line. If you vary the input signal a little bit, then your output varies according to that. Does that make sense to everyone? All right, let's take a pause. Let me know if you have any questions, and then we'll take a break. If you have no questions, you can take a break. Any questions from anyone? Yes. Because you're not applying 1000 volts externally. if your power is only coming from 110 to 120 volts, the maximum limit would be 110 to 120 volts. It cannot come from thin air, right? That's a good question. That's basically what, the purpose of this example is. Doesn't matter what your amplification is, the energy for that cannot come beyond that. And so that also is why we call this the saturation region, right? It saturates at a certain level, meaning the floodgates are wide open, everything is coming through. So even if the amplification factor is 1,000, we are not going to get 1,000. The transistor is going to saturate. It is going to saturate at the level of the supply that we're connecting to it. If that power supply that we're connecting to is 10 volts or 12 volts, maximum you would obtain is 10 volts or 12 volts. It saturates at the level of the power supply, right? Otherwise, we could solve the world's energy problem right there, right? If somebody could figure that out. We just create amplifiers, power supply amplifiers, and power everything. But that's not the way it works. Okay, so it's 10:56. Let's take a break. We'll pick up again at, let's say, 11:01, 11:02, about 5 or 6 minute break. In the meantime, I'm still here, so if anyone has questions, feel free to ask.